Welcome, everybody. As you said, my name is Aaron, and I'm going to be the instructor for this short course. My co-instructor is Sierra, who, as mentioned, is somewhere around, but not in the room right now. She's going to be giving one of the lectures later in the week. There's a syllabus available to all of you online. There are also copies in the back for you to grab on your way out if you feel so inclined. The meetings are going to be all here for Mountain View people, but the other locations may be dancing around a bit, so check the syllabus for that. The way this course is going to be set up is as a series of 5 lectures. This first lecture is going to be primarily introductory material. What is distributed computing? How do we approach it? And some background that if you had taken an operating systems course already, might be something of a review for you. But it's important to get everybody on the same page. The next 2 lectures are going to be on the more technical topics like MapReduce and GFS themselves. And the final 2 lectures are going to be more of an algorithms theory presentation. We've taken some algorithms which are important in distributed computing, and we are going to show how we go about reformulating these in a form that MapReduce can understand and utilize efficiently. So in terms of course expectations, every night we're going to have a reading. We will email out to you the link for the reading through the course mailing list. And there will also be some short homework questions associated with each of these. We don't expect too much, just a paragraph or so to help you gain an understanding of the material. And there's an email list that you should send all these to, which we'll be collecting and perusing. And as a reward for doing all your homework, we've got free t-shirts coming for everybody. But you still have to do the homework. So without further ado, let's get right into the material itself. We're going to start today, as I said, with an introduction to distributed computing, a brief digression on what separates distributed computing from parallel computing, a brief history that is going to show, very brief history, 3 slides, 5 minutes, that is going to show just the most important topics and how distributed computing evolved into the form that it is today, and then, as I said, into some operating systems background. So with a show of hands, who's heard of Moore's Law? All right, excellent. So Moore's Law states that the density of transistors on a chip will double every 18 months for approximately the same cost. As a corollary to this law, the frequency of CPUs seems to roughly double every 18 months. This law was observed, of course, by Gordon Moore, the co-founder of Intel. And for about the last 40 years, it seemed to be holding actually very steadily correct. But if you look at the extreme right edge of the chart, which shows the last 2 years or so, you will notice that the curve abruptly flattens off. There are a couple reasons for this. Transistors are very tiny now, measuring in single digits of atoms thick. So we are starting to approach physical limits on just how small we can fabricate chips. Another big problem is that memory bandwidth is now the rate-limiting component of computers. So even if we could develop a processor that could run at 6 gigahertz instead of 3, it would just be spending that much more time waiting for data to arrive from memory for it to actually process. As a result of this, developing faster CPUs isn't even really necessarily in our best interest in terms of speeding up our performance. So the upshot of this is that the scope of problems that we can solve with a single computer is not going to get dramatically larger anytime in the next few years. However, if we want to get more work done computationally, which we always do, we can still get through this by hooking up our computers to more computers. So since our transmission systems like Ethernet, gigabit Ethernet, fiber optic, InfiniBand, etc. are getting better, it's getting cheaper and cheaper to hook up these multiple computers together. So if we wanted to double the work that we can do, instead of waiting for a computer to get twice as fast, since that's going to take a while, we should just hook up 2 computers next to each other and give each computer half as much work. Obviously, this isn't entirely the case. If we provide 2 computers, we're not going to get an exact factor of 2 increase. However, the amount of work that we can do will roughly scale linearly with the number of computers that we hook up into a properly designed distributed system. So there's a bunch of questions on the board. Who can tell me any examples they can think of for these? Somebody start. OK, I'll just throw one out. For a single computer case, you can do anything that you want with a GUI, right? You don't need two computers to do a GUI. In the back. With 100 computers, we can multiply giant matrices. Yes, matrix multiplication is actually a very well-studied parallelizable algorithm. And big matrix multiplies are definitely the domain of distributed networks.
You could also play network games with them.
That's actually an excellent point. She said that you can do network games with multiple computers, with 100 computers. And if you think about it, World of Warcraft really is a giant distributed system. We have different pieces of the problem computationally of playing the game being spread out to all sorts of different machines across a network. So a few other answers is that with a single machine, we can compile any reasonably sized program. We can play chess reasonably well. If we have something in the neighborhood of several dozen machines or 100 machines, we can play chess really well. IBM's Deep Blue was a 30-way parallel system. Other things that are important are large-scale weather simulations and fluid dynamics and other scientific computing. And of course, as we all know here at Google, with an entire data center, you can, say, download some measurable percentage of the web and process it. So a few more examples, very briefly, of distributed programming. Movies such as Shrek use distributed computing to render the individual frames of their of the entire movie. In Lord of the Rings, they simulated entire battles of upwards of 50,000 individual virtual actors. So there were actually multiple computers deciding which orcs and elves should be throwing swords and arrows at one another by using a distributed network. And of course, on the less graphically glamorous but no less important side of things, Google uses distributed computers to index the web. Academics in a consortium called Planet Lab use a distributed network to simulate the internet. So if they want to design new algorithms like, say, a new version of BitTorrent, rather than try to run these experiments on the real web, which has all sorts of unknown variables, they can precisely control these factors through this virtual network that they've created on top as a distributed platform. And another company called Akamai uses distributed computing to make data available across the web at a high performance rate. So for example, if you want to go to a very popular website like CNN.com, if you're in Mountain View or New York City or in Berlin, you don't want to have to wait for all of your requests to go down to CNN's headquarters and come back. So Akamai's network makes cached copies that are local to individual users and routes your requests on the fly. So who can tell me what is the key attribute that all of these problems that I've just listed have in common? Any guesses? OK, they're all web-based, but not really. I mean, Shrek isn't very web-based, right? Oh, I'm sorry. Of all of the last several slides. Yes?
They're pretty easy to chop up into a bunch of more or less independent pieces.
Exactly. He said it is easy to chop these problems up into independent pieces. So for example, if we're rendering a movie, the individual frames are not dependent on one another. We have what the scene looks like and the representations of the models that become the scene separated through time. And the individual pixels that make up frame 10 have nothing to do with the pixels that we would see in frame 11 of this movie. So that way we can render those two frames at the same time. And in other words, what this means is that we do not have a data dependency between these subproblems. And for example, if we're rendering a battle, what happens on the entire left side of the battlefield has very little to do with the people fighting on the right side of the battlefield. So those don't need to be processed at the same time. You can have sub-battles being processed individually. And sort of by definition, Akamai needs to have multiple computers spread out and serving different web pages. Now, as promised, a brief digression on parallel versus distributed computing, because these two terms sound very similar, and they mean inherently similar things. It's doing multiple pieces of work at the same time. However, the key difference that you should keep in mind is that parallel computing is all restricted to within one computer, even if there are multiple CPUs inside that computer. So all of these CPUs are seeing the same copy of memory. In distributed computing, we've taken these multiple CPUs and moved them into separate computers that are interacting across a network. So when we have a network involved, there are more, not problems, but certainly concerns that must be addressed when we design our total system. So to briefly motivate why we do distributed computing the way we do today, it's important to look at what we tried and where we are coming from. So in the early 70s, computing is starting to really take off. Everybody's kind of sold this might be an idea worth throwing some more money into. And people were coming up with data to process far faster than we actually had computing power to process it. Especially once we got into scientific applications, if you try to hook up a computer to, say, particle accelerators, they generate massive quantities of data that need to be all parallelized, or I mean all processed. And this data processing can be done in pretty much the same way. We have several different pieces of data that all need the same series of instructions applied to it. So while the initial model for a CPU is something that takes some instruction I and moves a piece of data through the instruction, they said, well, it's very complicated to have multiple instructions operating at the same time. So instead, what we should do is we should just load a whole bank of memory into the CPU at once. So it looks something more like this. We have one instruction I being applied to several different data elements. And the way we do this is by using a for loop. You can say, and if we write code in this style, for people in the back, is this large enough? Great. So if we write code in this style, it's very clear that we have 100 addition operations to run. And we would write code in for loops, and compilers, which were specially written to be parallelizing compilers, would recognize that we are doing the same operation across a range of memory. And it would just load the whole range of memory into the instruction at the same time. So Cray was one of the companies that was most involved in supercomputing at this era. The picture on the slide is a Cray 2 supercomputer, which, for a sense of scale, is about the size of your coffee table and as tall as I am. And it got a lot of speed up through vectorization. However, they weren't able to keep this going into the limit. So by the time the early 80s crept around, we realized that we can't make a single vector CPU like that much faster. The Cray XMP, for example, had 4 Cray 1s bolted side by side inside the same box. So what this means is that as we left the 70s into the 80s, vector parallelism was still important, but thread-level parallelism was starting to gain its prominence, because we would have another vector machine down here in the same total machine running a different instruction I prime across several different inputs. Question in the back. How big are the vectors? I am not entirely sure. I believe a common size was 32 words. So as we moved into the 80s, there were all sorts of other companies that billed themselves as supercomputing companies. And the architectures that they developed, they banded under the term massively parallel. And what they were actually doing was early clustering. They were taking multiple machines together and stringing them through a common interconnect. The major problem in this era was that we did not have much bandwidth. Think about the technologies like Ethernet that existed in the 80s, like 10 megabit Ethernet. Even in the 80s, it's not that hard to conceive of making half of that, or not half, I'm sorry, 10% or so of that get taken up by a single machine. But that means that as soon as you put 10 of these computers on the same network, they've already filled the pipe. And getting the data to individual machines was a struggle. You have to think very hard about what is the minimum amount of traffic that you can use to accomplish your computation. There are also some other interesting architectures going on. A British company named Kendall Square Research arranged several processors in the same machine in a series of concentric rings. So the inner processors would receive a set of memory to process. They would run their code over it. And then there was a button sort of that the code would push, which would shift that bank of memory to this outer ring of processors, which would then do the next stage in the pipeline. And a new set of fresh data would go to the inner ring. As you might imagine, this is really weird to actually compute. Like, how do you write code for such a system? So libraries were starting to be developed, one of which was called the Message Passing Interface, or MPI, to help programmers make these different architectures work. MPI is still actually used today in a lot of parallel programming and distributed programming. And in the final era, we bring ourselves from 1995 through today. And so while the supercomputing years led to a variety of different architectures, which made interesting decisions, all of these one-off designs were getting really expensive. So nobody wants to spend $10 million on some large supercomputing system from Cray, when they realized that you could buy several COTS or consumer off-the-shelf machines and just link them all up in parallel. So 32 white box computers with Intel or AMD CPUs, for example. So companies like Google actually start taking this to the extreme and using several small servers. And Google is famous for not using large special purpose supercomputing hardware. And across the rest of the web as well, we're seeing that individual home PCs can be used in a supercomputing platform. Berkeley, for example, has the SETI at Home project and several others that actually create these web-wide clusters out of individual users' PCs. So at this point, we're going to change tacks and move to the question, what is actually involved in parallelizing a problem? And really, the idea is deceptively simple at the highest level. We take some amount of work that's a set of distinct problems, we break it off into as many units as we have processors, and we push the work out to them. And the way we push work to different processors is by spawning different threads, which are going to run on them. And each thread then receives some unit of computation from our master program. So a thread refers to a separate unit of control. Effectively, it's its own call stack of functions that are being run that don't need to return before the main program continues. So if we have our main call stack, and we call some other function that goes here on it, we need to wait for that function to return before main can actually execute the next step. But if we spawn a thread, then the spawned function is going to go in its own separate stack, which is operating independently of the initial stack. It's also important to realize that you can run the same function in several threads at a time. So again, if we wanted to render Shrek, we might have a function named render1frame. And we would call several copies of render1frame, which would each be given a different argument indicating which frame it should actually be computing on and determining the pixels for. So now that we've spawned our threads, we have our work partitioned. We just move the work into the threads. They compute it, which obviously turns things from red to green. And then we would take all of our results and aggregate them back to the master thread, who is waiting on all of these subthreads to continue. Of course, this sounds awfully straightforward. But it raises a whole bunch of questions. How do we actually assign these work units to threads? What if we have more work units in threads? How do we aggregate the results at the end? If we have a bunch of render1 frames going on, for example, and frame 100 is finished and frame 1000 is finished, how do we make sure that when we write this all out to the movie file, frame 100 arrives before frame 1000 in the file, and presumably roughly 900 frames, give or take, in the middle? So to the bottom question, what is the common theme of all these problems? Anybody have an idea? Communication. Yes. Each of these problems represents a point where multiple threads either need to access a shared resource or communicate with one another. And the way that communication or shared resources are always represented is obviously through memory. And anytime multiple threads need to use the same block of memory, we need to use something called a synchronization system, which allows us to control the order in which this memory is accessed. So the next few slides are going to motivate with an example a few synchronization systems that we use in multi-threaded programming. So here we have a program with two threads, and they have each just entered a function named foo or bar. And we have two shared variables, x and y, and we have these simple assignments that are occurring in them. So if the initial state is y equals 0 and x equals 6, what happens when we run these threads? Who knows, right? There's about a dozen different possible outcomes. We can have 7, 9, or 10 for x. We can have 1, 7, 10 for y. We don't know which combination is actually going to arrive. The reason is because things that look like single steps, like increment x, actually take a whole bunch of steps if we were to compile them. So, for example, the increment operation actually gets compiled out to 3 separate operations, where first we load x from memory into the CPU, operate on it, and then write it back. But whenever we load the memory out, some other thread could have updated it before these other 2 operations have run. So we don't really have a way of determining or detecting which order these threads are going to run in or how they're going to be interleaved. The term for this is called a race condition, because each of these threads are racing to complete. And depending on who wins the race, we get a different outcome. In general, this is bad. And more problematically, it applies to more than just integers. It applies to our higher level data structures as well. For example, it might be possible for us to have a linked list class. So we have a reference to the head item in the list, and we might also have some field called count, which tells us how many items are in the list without having to actually traverse it. However, if we were to insert an item into this list, we would have to do 2 things. We'd have to increment the counter, and we'd also have to patch up the reference to the head of the list to include the new element. And if one thread is busy doing both of these, then another thread might come in, see the list, and get the wrong count at the same time, which, depending on how we wrote our program, might cause a crash. So, in general, any time that we need to operate on anytime we need to perform an operation which is going to take more than one step, we need to use a synchronization system. Synchronization primitives are represented to us as shared variables. And the guarantee that is made with synchronization primitives is that they can only be accessed atomically, which is to say, indivisibly, in one step. And the way we guarantee this is by special hardware operations that perform the update to the synchronization primitives in one step as seen by other threads. So for example, the processor might lock down the memory bus so that other threads cannot continue with their reads and writes while the atomic operation is in effect. So synchronization primitives can be motivated with a real-world example. If we were to develop a network of train tracks, we'd probably want to have 2 of them running at any time, one going east, one going west. But if we have a shared resource, like a bridge, that might be really narrow, you might only be able to run one track over the bridge. So in the image we have here, we have tracks moving right and tracks moving left, but this shared element in the middle has traffic that goes both directions. And it would be really bad if freight trains were to come screaming into one another in the middle of the bridge. So the way train engineers solve this problem is with a set of flags called semaphores. And there would be a semaphore flag at each side of the bridge that are initially both set to green. When a train comes to one side, there's a lever on that side that can be cranked, and it will set the flag on the other side to red. Then, anytime a train comes, it has to wait for its flag to be turned green by the engineer who's allowed to pass his train through. So a key feature is that the way the engineers respect the flags, two flags can never be red at the same time. Two flags can both be green, indicating that the shared resource is uncontested. However, if one flag is red, that engineer has to wait for him to be allowed to proceed. So how does this relate to computer science? We can think of set and reset as lock and unlock. And if we were to have a lock object, then you can lock the shared resource by calling lock, modify the shared memory, and then unlock the lock when you're done with it. A key point is that two threads can obviously never hold the same lock together. So if one call to lock proceeds through, the other call to lock blocks, which is to say that thread falls asleep. So things we have to keep in mind when using locks is that we have to keep our locks consistent. We have to use the same lock every time for a shared variable. So if we have some int x, we might have two locks lx and ly. And as long as we always lock lx when modifying x, we're fine, especially if we unlock lx when we're done modifying x. However, nothing prevents you, compilation speaking, from writing code that locks ly and then modifies x, which is still going to introduce the race condition from earlier. So to go back to our example, we can create a semaphore object named sem, which is going to guard access to both x and y in these two threads. So does this solve the problem? Who thinks it does? Yes.
Which problem?
That x and y can have the question is which problem, and that would be that x and y can have multiple final values. So semaphores have prevented both threads from manipulating x and y at the same time. However, they are not sufficient to ensure that there's only one total flow that can modify x and y. And the way we do that is with a condition variable. In the Windows programming environment, condition variables are also called events, because they are used to signify from one thread to another that some event has taken place. So, for example, if we had a queue where we are sending elements from one thread to another, if the queue is empty, then we would like the dequeuing thread to fall asleep until the event occurs that the queue has been refilled. So in terms of the example that we have earlier, we want to notify threads when foo has finished so that bar can continue, for example. So where semaphores had the lock and unlock primitives, the condition variable objects have two functions called wait and notify. Waiting on a condition variable obviously makes your thread fall asleep, and then notifying the condition variable will wake somebody up who was initially waiting. So to complete the story with the example, if we want foo to finish before bar, we would have to introduce two new variables, a Boolean that we call foo is done, and a condition variable that's called foo is finished CV. The reason we need both of these is because notifications are one-shot objects. If nobody is waiting, then the notification just sort of goes to nowhere, and you won't be able to realize that it happened. So we need two variables, a persistent Boolean and the condition variable. So if bar were to execute before foo, it would achieve the lock, it would realize that foo is not done, and then it would wait on the condition variable. And it passes the wait function as a parameter the lock that it holds. So it will have to release the lock, which will allow foo to acquire the lock and continue. And then when foo notifies bar, the notify will wake up the wait, and it will reacquire the lock to proceed as follows. And so now we've actually communicated a serialization order from one thread to another. A major problem with synchronization, though, is that we need to synchronize, as I said, every time we have shared state. And each time we synchronize, we have more locks coming in, more events that need to be handled. And if you program things slightly incorrectly, you can cause the entire system to get stuck. As I said, functions can be called in any interleaving between two threads that are running in parallel. So if thread A locks semaphore 1 and thread B locks semaphore 2, then when we start trying to execute the second two lines, we're going to have big problems, because neither thread realizes that it should back off. So we have a condition called deadlock, which is similar to the traffic jam in this picture. None of the cars can move backwards because there are cars behind them, so they can't unlock an intersection. But no cars can move forward because, again, there are cars in the way that are waiting for another intersection to be unlocked, so to speak. The moral of all of this story is that synchronization is really hard, and that we need to synchronize all of the shared state across our program, and we have to keep our locks meticulously organized. The cheating way out, obviously, is just to have one big lock, and every time you have shared state being manipulated, you lock it. But this would totally slow our program down because we'd effectively be running as fast as only one thread anytime shared state is entered, which on any distributed system is going to get relatively large relatively quickly. So what we would like to do is keep our shared state to a minimum. And MapReduce, the system we're going to discuss in tomorrow's lecture, gives us a programming paradigm that eliminates this need for us by doing all of the locking under the hood and asking us to phrase our programming problems in ways that eliminate shared state. Any questions about synchronization before I proceed? OK. So while the previous slides applied to problems in both the parallel and distributed worlds, when we move purely into distributed computation, we have to take into account the network. And while we access the network through a series of abstractions, it's important for us to understand what is occurring underneath of these abstractions so that we can design for robustness in our distributed systems. Because when we start doing really high-load programming, these abstractions start to break down and cause problems. So the most basic abstraction we have in the internet is something called a pipe. And we like pipes because they look a lot like files. A file has 4 operations that we can do on it that are important for purposes of this discussion: open, close, read, and write. And if we have a file, whatever we write into it is exactly what we read out afterward. A pipe looks like a file to a programmer because it has the same 4 operations: open, close, read, write. However, a pipe is, by definition, bidirectional. So whatever you write into one side of the pipe can be read from the other side of the pipe. And obviously, anything that gets written in here is read on that side. So you cannot read back what you have written. Sockets are what happen when we take a pipe and stretch it so far that instead of running between 2 processes on the same computer, it's running over the network. And the way that we use sockets is by connecting them to the remote machine through its IP address. But an IP address alone isn't really enough for us to specifically identify where we want our pipe to hook up. For example, on my computer, I have web, email, instant messenger, probably a few SSH sessions, maybe an FTP all running at the same time. And if we just had one pipe connected to my computer's IP address, all of these different connections would be funneled together and would cause garbage, right? So instead of just using an IP address, we actually use sub-addresses within the computer, which we call ports. And a port is just another number that we add on to the end of our address that identifies which program we want to use to receive the traffic. So when you connect to a website, for example, like www.google.com, we don't actually give a port. Our computer just translates this through DNS into an IP address And we know that web traffic likes to be on port 80 because that's an internet standard. However, in our address, we could also specify with a colon a port number to use. So if we wrote an IP, if we wrote out a URL like this, it would try to connect to port 1000 on this computer. Another important thing to remember with ports is that even if we have all of the web traffic going to port 80, for any real website, there are going to be several requests coming at the same time. So we still haven't solved the problem within one program of having all sorts of traffic coming into one pipe. So what actually happens is that while port 80 is where we listen for traffic, when we actually make the connection, it's broken off into a separate pipe that is connection specific, that's given its own anonymous port number. So that way we have one port connecting a single, one port and one pipe connecting a single client to a single program running on the server. So underneath the hood, how do we actually connect to ports and sockets and all that? And the way we do so is, while the pipe just looks like a big stream of bytes to you and me, who are the application writers, the operating system under the hood is wrapping your protocol inside a set of network layer protocols. The two most important of these are called TCP and IP, and they're used together so often that we just refer to them as TCP/IP. And it takes your particular stream of data and wraps it inside headers from these two protocols. The IP header provides addressing, so it actually says that we should be going to a particular IP address with this set of data. And that would be enough if our network was reliable. But it's not. For example, if you're connecting from your computer here to some computer in New York City, there's a router that it has to go through in Kansas. And there's a lot of potential for power failures and fires and all sorts of problems to hit Kansas along the way between here and there. So instead, to combat this, we add the TCP, Transmission Control Protocol, to the mix, which provides us with some reliability information like sequencing. So every packet that your system sends has a number attached to it. And they're all in order. It'll say 5, 6, 7, 8. And if we see packets that go 10, 11, 13, 14, we realize that we've missed packet number 12, and the system can ask for that data to be resent. And the operating system will, under the hood, patch this up so that you just see the continual stream of bytes, 10, 11, 12, 13, 14. This is really important because whereas we see it as a big pipe, underneath the hood, it's actually a big mesh. The phone system actually is circuit switched. When you make a phone call from a landline, the routers that are involved in this network actually will designate a particular physical connection to carry your traffic and your traffic alone. And the reason that very long distance phone calls may take an extra second to set up is because there's a series of routers along the way that are figuring out a route to use expressly for you. The internet, however, doesn't obey this policy. It just starts sending packets outward. So to balance the load, for example, the router most close to you might start sending your packets on all the different routes that it has available to it until it discovers the best route. But of course, if one of these routes is a lot faster than this other route, say this one goes through Alaska and this one doesn't, then these packets are going to arrive ahead of time with respect to these ones. So that's why we need things like TCP to help us patch this up. So to break this down, why do we actually need to learn all of this stuff? Why, since we can just see the pipe, why can't we just use the pipe as is? But there are several issues that are going to be relevant to us as distributed systems programmers. For example, what does it actually mean to disconnect in a packet-switched world? All it really means is that your computer has stopped sending packets through the mesh. There are special packets that can be sent that will tell the remote computer, by the way, this is the last one. And then that computer can explicitly deallocate its resources. But really, how is a disconnect any different than a really long gap in transmission? What if our computer crashes? Is that a disconnect? What if one of the routers in the middle catches fire? Is that a disconnect? It's hard to determine when the conversation is over. Also, from the perspective of the sending party, how do we know how much data they've received? Since TCP gives us sequence numbers on our data, it also gives us acknowledgments back. So if you've sent packets 100, 101, 102, the remote end will then say, here's a packet that says, I've received your packet 100. But if you don't get those for 101 and 102, did they not get there? Did their computer crash before we received 102? Or did they crash after they received packet 102, completed the financial transaction, wrote it to disk, and then was about to send the acknowledgement when all of a sudden the power went out? And so if we're going to design reliability into our distributed systems, we can't allow network hangups like this, which happen all the time, to bring our entire network of 100 or 1,000 or maybe 10,000 machines down. Because in any network that's going to have 1,000 computers running on it, at any point in time, one of them is going to have a hard disk that crashes or something. And our entire system needs to have higher level protocols built into it that offer us guarantees on how much data got processed and explicitly define what happens if we do not reach each of these checkpoints. If we also refer back a bit to this graphic, the way TCP/IP works is it takes whatever bytes you put into the pipe and it just writes more bytes in front of them, telling every computer that it can see that it should forward this middle packet in the envelope. But there's nothing that prevents those other computers, which are necessarily reading the IP address information, from also reading the rest of your data. So if we want to design a distributed system that is going to work, say, across the public internet and not inside our corporate intranet, we have to trust every router in the middle, which isn't likely, or we have to build our own protocols in that will encrypt our traffic so that they can read the IP headers, but not the actual data that's marked in blue here. Furthermore, these other routers might be willfully malicious as opposed to simply eavesdropping. Since they can see the TCP sequence numbers that are moving through, it might be possible for one of them to say, oh, I've seen packet 100, here's packet 101, here's my packet 102 instead. And the other computer gets packet 100, packet 101, 102, and says, oh, here it is, good. And now they've totally subjugated your data. So we might also need our own protocols to ensure the authenticity of each packet and guarantee that it came from the host that we claim it does. And finally, if we have a packet-switched network, that means that the routers are going to have to be working to interpret where all of these packets are going. And if we have our routers set up intelligently, then they can forward data along routes that minimize the total crossover traffic. But if we have a network inside of our cluster that has several machines over here that communicate and several machines over here that communicate, we might want to develop an intelligent topology for our routers that puts a router here and another one here, as opposed to just having one that all 8 machines share. That way, traffic from these 4 will not bog down the computation being shared by these 4. So if we're going to develop a system all the way from the ground up, we have to start at the link level. So to conclude the lecture, processing more data is going to mean using more machines at the same time. That's because Moore's law has pretty much maxed out, mostly because of the memory bandwidth issue. Anytime we're going to cooperate between multiple processes, we have to use synchronization primitives, which start having problems such as deadlock and race conditions and trying to debug these issues that come up maybe one run out of every 50,000. And whenever we're going to design a real distributed system, we have to consider how all elements of the system, such as the network topology and the ability for individual components of our distributed system to fail, come into play. So the next lecture is going to talk about how MapReduce itself works and how it obviates a lot of these concerns for us so that we can concentrate on actually getting our interesting computation done on top. At this time, we can open the floor for questions.
Is this mic on? You can hear this?
All right. There's questions. I've got a mic. I can run around the back.
Can the remote offices, are your mics unmuted now? Okay, inquire. Okay, inquire.
Any hands? Any hands? Whoa.
Kirkland is unmuted.
Is that a hand? Somewhere in the big picture? Somewhere in the big picture? No. Okay. No. Okay.
What's going on?
No questions? No questions?
Great.
All right, call it a deal. All right, call it a deal. Thank you, Okay, really quick, why everyone is still here. So we're going to be taking care of all the video conferencing from here out. I think I said that, so you don't need to worry about it. Just make sure that you communicate well with me and that your course, your room that you'd like to have video conferenced in is on the syllabus. And if the room that you want us to video conference in is not on the syllabus, you should email Aaron and make sure he puts it on the syllabus, and then I will make sure that the video conferencing people have this before all of our lectures. So, all right, everyone, we will see you tomorrow.
Hard copies of the syllabus are available back there if you want them. We'll email out the reading and homework very soon.